Welcome to the Deep Dive, your shortcut to getting up to speed on fascinating topics. Today we're going to dive into the world of integer sequences, specifically a really interesting generalization of the Fibonacci numbers.
That's right. And our focus today is on a specific sequence from the OEIS, the Online Encyclopedia of Integer Sequences. It's sequence A000288. For those maybe less familiar, the OEIS is basically this huge database, like a Wikipedia for number sequences, indispensable for mathematicians.
Right, a vital tool.
Our mission is really to shed some light on the sequence's unique definition, some of its, frankly, surprising properties, and, why it's worth studying.
Okay, so let's unpack that. Fibonacci numbers, most people have heard of those. EG number is the sum of the two before it. Tetranacci, though, that pushes it further.
Exactly. Tetranacci numbers follow a similar idea, but instead of summing the two preceding terms, you sum the four preceding terms. So the basic rule is Tn equals Tn1 plus Tn2 plus Tn3 plus Tn4.
For n greater than or equal to 4, I guess.
Yeah, precisely, yes. For n equals 4. But here's the fascinating part. That recurrence relation is the same for all tetranacci-type sequences. But different starting values create completely different sequences.
Oh, okay. So what are the specific starting values for this sequence, A000288? What makes it unique?
Right. For A000288, the sequence kicks off with A000000 and 1, A2 was 1, all ones.
Just ones, okay.
Yeah, so the sequence goes 1, 1, 1, 1, then the sum is 4, then 1 plus 1 plus 1 plus 4 is 7, then 1 plus 1 plus 4 plus 7 is 13, 25, 49, and it keeps going like that.
And you mentioned this is different from the standard Tetranacci number.
It is. The sequence, often just called Tetranacci numbers, is OEIS A00000008. It starts 0, 1, 1, 2. Same rule, adding the last four terms, but those different initial values send it down a totally different path.
Okay, got it. Now, you mentioned A000288 has some really surprising properties.
Yeah.
What's one that stands out?
Well, one of the most remarkable, I think, is its combinatorial interpretation. It sounds a bit complex, but stick with me. The term an plus 2 in this sequence, it actually counts the number of ways you can create words of length and using only the letters 0, 1, 2, 3, but with a special rule.
A rule, okay. What's the catch?
The rule is, whenever you use the letter X, so 1, 2, or 3, it must be immediately followed by at least X zeros.
Oh, wow. So 1 needs at least 1 0 after it, 2 needs at least 2 zeros, 3 foot needs 3.
Exactly. And the number 0 can be followed by anything. The fact that this simple-looking sequence, 1, 1, 1, 1, 4, 7, actually counts that specific combinatorial object is, well, it's quite amazing. It connects arithmetic to structure.
That is unexpected. Does it have other interesting mathematical behaviors, like, say, how the digits behave?
Yes, absolutely. That leads to another fascinating point, its distribution. A000288 actually satisfies Benford's law.
Benford's law, right?
Yeah.
That's the one about leading digits, where 1 is more common than 2, 2 more than 3, and so on, in many real-world data sets.
Precisely. Things like populations, river lengths, financial data often follow this pattern. And the fact that this purely mathematical sequence, A000288, also follows it suggests its growth pattern somehow mirrors these natural phenomena. It's a deep connection.
That's wild. So it connects to combinatorics and even statistical laws found in nature. What about the growth rate itself, like how the ratio of terms behaves?
Ah, yes. Like the Fibonacci sequence ratio approaches the golden ratio. The ratio of adjacent terms in any Tetranacci sequence, including this one, converges to a specific constant.
Which is?
It's called the Tetranacci constant. It's approximately 1.92756. And this isn't just some random number. It's the positive real root of a specific polynomial equation. By 4, by 3, by 2, by 1 is 0.
Okay, so the polynomial is fundamental to these sequences.
It absolutely is. That root dictates the long-term growth factor. And related to that, A000288 has its own specific generating function.
Right, that's like a compact formula that holds the whole sequence.
Exactly. It's a power series where the coefficients are the terms of the sequence. For A000288, it's 1 by 2, 2 by 3 divided by 1 by 2 by 3 by 4. That denominator, 1 by 2 by 3 by 4, is directly related to the recurrence relation itself. Generating functions are incredibly powerful tools for analyzing sequences.
So wrapping this up, thinking about this sequence, A000288, what's the big picture takeaway for someone exploring number theory?
Well, I think A000288 is a beautiful example of how complexity and richness emerge from simple rules. You start with a basic recurrence, add the last four terms, change just the initial conditions, in this case to 1, 1, 1, 1,
Hmm.
and suddenly you get a sequence with these surprising links to combinatorics, satisfying Benford's law, connected to this specific tetranacci constant. It really highlights how subtle changes in definitions can open up whole new mathematical landscapes.
It really makes you think how slight variations can lead to such different and intricate structures.
Precisely. And it encourages you, the listener, to ask, what happens if you tweak the initial conditions of a known sequence? Or slightly alter the recurrence rule? What undiscovered patterns might you find?
A fantastic question to ponder. It really shows there's always more to explore.
Always. That's the beauty of mathematics.
A perfect thought to end on for this deep dive.